Welcome to one of the most exciting topics that we have in DVCon on day one, which is nothing but an introduction to Accelera portable stimulus standard, right? So we have been hearing about it across the last 2-3 years, but now I believe the draft standard has been released, and a lot of you are eagerly waiting to hear about what's next in Accelera PSS standard. And for this particular tutorial, we don't have one, we don't have two, we have 6 speakers, all experts in the field who are going to come and talk to you about this standard. And I've been given the honor of introducing them. So thanks. Earlier when I usually kind of hear the introduction, it's like, okay, I mean, why this long boring thing and stuff like that. But then I realized that each one of their introduction carries a story, the story of how they got there and what fields they have kind of specialized in. So I'm going to be introducing the speakers to you. If I may, as I announce, if you could please just stand up, face the audience and sit down, then I'll continue, okay? So the first speaker is Sharon Rosenberg. Sharon? Okay, you can just raise your hand. Thank you. So Sharon Rosenberg is a senior architect at Cadence. He has received his BA in computer science from Bar-Ilan University, and he joined Vericity Design in 1996 to lead the hardware test bench automation revolution. Sharon introduced many of the most used UVM concepts, including agents, factory, configuration mechanism, and sequences as the technical manager of Cadence UVM team. Sharon represented Cadence in the Accelera UVM working group and co-authored the book, A Practical Guide to Adopting the Universal Verification Methodology. Currently, Sharon is driving software-driven methodology for SOC verification and represents Cadence in the Accelera Portable Stimulus Working Group. Welcome, Sharon. The next speaker is Karthik Gururaj. Karthik? So, Karthik Gururaj is currently the principal architect at Viavia Labs Private Limited. He has over 16 years of experience in virtual platforms and embedded systems. He has led several standardization activities in his previous organization, NXP Semiconductors, and has contributed in the OSCE TLM working group, now part of Accelera. He holds a BTech honors degree in electrical engineering from IIT Kharagpur. Welcome, Karthik. So the next speaker is Bishnupriya Bhattacharya. Hi. So Bishnupriya is a R&D director at Cadence Design Systems, Bangalore. Her areas of interest span across ESL simulation and verification and the emerging portable stimulus specification. Throughout her career of 20 years in EDA, Bishnupriya has been actively associated with Accelera standardization committees and has made significant contributions to Accelera standards, including System C and the recent portable stimulus early adopter. Bishnupriya has published in prestigious peer-reviewed conferences and serves regularly in their technical program committees and steering committees. She has also co-authored a book on UVM mixed language. She obtained her BTech in computer science from Jadavpur University and her MS in electrical engineering from University of Maryland, College Park, USA. Welcome, Bishnupriya. The next speaker would be Srivatsa Vasudevan. Hi. Srivatsa Vasudevan is a principal engineer in Synopsys Incorporated, where he works on cutting-edge methodology and technology in verification solving problems using next-generation designs. He has written 2 books on verification. One is on test planning titled Effective Functional Verification, and a popular book called Practical UVM. He is a member of the Portable Stimulus and UVM Accelera committees. Srivatsa brings in experience from a number of semiconductor sectors, ranging from CPU design to networking to wireless devices, having successfully taped out a number of designs at various companies over the last 2.5 decades. Welcome, Srivatsa. Next is Pradeep Salla. Hi, Pradeep. Pradeep manages the verification team at Mentor Graphics, a Siemens business. He is responsible for driving and supporting the verification technology team and also develop markets for Mentor Graphics in India. Prior to Mentor Graphics, he has worked in various organizations such as Renesas Electronics, Nokia, and Mindtree, and has a total experience of about 14 years in functional verification. He received his master's in electrical engineering from North Carolina State University and BE from Bangalore University. His area of expertise includes architecting reusable test benches at IP, subsystem, and SOC level. He is a regular speaker at...
Okay. Where is that? Okay, great. Because I was looking at the screen and didn't have anything on it. So my name is Srivatsa Vasudevan. I'm basically here on behalf of the Accelera committee to introduce to you the Accelera Portable Stimulus Standard. I'm just going to go very quickly with a brief overview of what it is and what it is not, and I'm basically then going to turn over the podium to the other members who are actually going to go into deep details of what the standard is. So as we begin, I'm just going to, Swami already did the introduction, so I'm basically going to slip over the slide. So let's start with a brief history of verification. A long time ago, when people were doing gates, people wondered, what is verification, right? Okay. Eventually, I think you'll notice that, basic directed testing, people writing simple tasks, making sure at least something was working. I can remember a situation in one company that I worked in. They had 17 tape outs to fix one bug. Okay, that was a long, long, long time ago. Okay. Eventually, as time passed by, we used to see ad hoc verification teams. Ad hoc is in the sense, loosely, that if a designer got done with his blocks, he would then join the verification team trying to fix the other man's code. And, teams were ad hoc, the duties were ad hoc. You would also notice that it was not a fixed job responsibility. You invariably had other responsibilities as you went along. Okay? Then came system Verilog. Okay? You got CRV, you got metric-driven verification. Okay? What this did is it basically gave a sense of metrics of completion. And by this time, you'll have realized that the language itself became quite different from the regular structural synthesizable Verilog that we all know and love today. And it also gave birth effectively, I would call it this being the point at which you would actually see the birth of a pure verification engineer who only went ahead to verify the design. And he didn't actually concern himself with the actual design itself. Okay? That wasn't enough. And then over a period of time, what you noticed is that you noticed a number of people put out a number of methodologies trying to standardize the way in which the system Verilog was actually written. Okay? And so we had the birth of ERM, which was the beginning, which I think I'll give full credit to Sharon here for that. And then we also saw the birth of VMM, OVM, and UVM, which subsequently followed as system Verilog class libraries. So it hasn't ended there, right? UVM is now very, very popular. A lot of people use UVM. But we're going to discuss now that things have gotten bigger and bigger and bigger. Okay, they've gotten far more complex. Okay, and the needs and demands, if you guys attended Chris Tice's presentation this morning, you'll notice that things have gotten really big and you need a different approach in order to handle things. Okay, and as time has gone by, you also see an increase in verification productivity. And that brings us to what is portable stimulus. Okay. So what are we seeing today? You'll see a ton of IoTs, you see electronic self-driving cars, you see a whole load of things going on. The complexity is just beginning to explode. Okay. You look at a watch, or you might be wearing a wearable fabric that actually is fairly complex. And no matter what you do, it's going to be bigger than the verification problem. It's just going to be way bigger than that. And given the size of this problem, I think you will come to the recognition that UVM runs out of steam at that point. Okay? You've also got multiple platforms. If you've seen the talks this morning, you'll realize that there is an emulation component, there's a simulation component. There is also maybe a piece that you run with the tester, or maybe you're going to build a separate prototyping board. And here's the big challenge. As you go from one environment to the other, you effectively wind up writing the same tests sometimes. The intent of the test does not change. Right? Okay? You're doing the same things. So what's one way to get around it? A way to do it is using a higher abstraction layer. Okay? And then you might want to reuse some of your block level or system level tests. But guess what? You run into a problem, right? They're written in a different language altogether. Okay, maybe that language and its compiler doesn't exist in the platform that you're running on. So here you'll see on the side, you'll see either a simulation box or an emulation box or maybe a prototyping box. Guess what? What ran in simulation may or may not run on the emulation box, depending on the platform you're on. And most certainly may not run on the FPGA box, because clock speed is very different. You're not measuring individual clocks at that point. Things that you might see is that using UVM, although I just came from the UVM presentation, it's not that I'm pitching it there and not pitching it here or anything of the sort. I want you to recognize that there are two different things that are targeted at two different spaces, okay? You'll also notice that as far as SOCs are concerned, constraint random may run out of steam, just given the size of the problem. And as you go through this presentation, I'll be talking about coverage later in the end. You will also realize that the paradigm itself is actually quite different, okay? And C tests are usually useful in certain scenarios, okay? So now you've got a block subsystem and a full chip, and it's running on 3 different platforms, and you've got either a UVM in one side and a C on the other side, and they both have the same test intent, okay? You're testing the exact same thing. So that brings us to portable stimulus. Okay, the whole idea here is a single specification of a test intent. Intent, what is it that you're trying to test? That's common to all platforms, okay? It has constraint randomization, that's not something you'll find in C, okay? It allows you to model interactions, dependencies, resources, and a whole load of other things as part of the language specification, okay? And once you specify your intent, what fundamentally happens is that you allow a tool to accept your intent because it's written in a certain language, okay? And then generate the corresponding test for you. It's a layer of abstraction. And the tests are correct by construction because there's a bunch of constraints that you can feed the tool in order to produce the right output, okay? And the same intent, when run through the tool and can be retargeted to some other platform. And you may choose to link in additional target-specific libraries. Now, if you had to do it the old way, trust me, you would have had a ton of make files all over the place, okay? And then having to maintain multiple pieces. Here, you can model everything with one intent. It's a little bit of a higher level of abstraction, and you can get it to work. That said, let's go take a look at what it does in a UVM environment. We're not telling you now to go and rip out and throw away all your UVM sequences. It's also possible that you may write some brand new UVM sequences that have never been written before as compositions of existing sequences. So here you'll see the picture of a PSS model which has your intent, which then passes through a tool and then spits out a bunch of UVM sequences, okay? So the checks and other things and the coverage points are also translated downstream to what would compile using a system Verilog compiler, okay? And then you fundamentally got an intent that's modeled in PSS that passes through a tool and then lands up as an UVM sequence. That's not just it, okay? You can also have the tool, with some configuration. I'm not going to go talk about the tool at all, but you can fundamentally take the same tool, okay, and take the intent and then retarget it to produce a combination of both a UVM sequence and probably a collection of C tests, okay, depending on the way the tool maps it, okay? And you may reuse different pieces from different places. It's entirely possible that some of the sequences or C tests are actually composed of various little bits that come from various sources. Okay, so we talked about all this, right? We talked about the fact that it's huge, it's abstract, it's gone up there and all that. But there's a number of things that portable stimulus is and is not, okay? First and foremost, it's not a UVM replacement. Let's get that out of the way, okay? UVM is good at certain things, okay? It's good for block level and maybe subsystem level verification. It will continue to be so. It's become a IEEE standard as we go along. This portable stimulus is targeted towards larger problems. It's not a reference implementation. That's the other thing we want to clarify, okay? What portable stimulus is a way to model test intent. And you're going to learn a little bit more about this as we go along. It's not a fixed level of abstraction. It could be one of a different number of levels of abstraction. It's not a single piece, okay? It's composed of a number of parts. And it's actually two representations of the same intent, okay? You got a DSL language and a C++ that mirrors the DSL, and they are 1:1. I don't want you walking away from here thinking that they're two different things. They fundamentally mean the same thing. And the tools will consume both formats, okay? And it's not just stimulus. It's a modeling of your test intent, okay? At the same time, having said all this, the tool only allows, the current specification today allows you to model your intent. It does not place any restrictions on the tool, the platform on which the tool runs. Maybe it's a Linux or a Mac or a Windows. None of those things are actually a part of the standard. Okay, it's just a specification of what it is. That said, I'm going to turn this over to Pradeep. I think I drained the batteries out of this guy. Okay, you may have to point at that screen to get it to work.
Visible there? Okay, great. I can't see the screen, so I'm just going to point random directions. Okay, thanks a lot, Sriyatha. That was a good introduction of what portable stimulus is and what portable stimulus is not. Now, we're all engineers. Anyone who's not an engineer here? Okay, good. So what we really like, right? Looking at code. So I'm going to show you a bunch of code that a lot of our, we like to look at. So with that, let's look at some of the basic concepts and constructs that we have with portable stimulus. So to get started, here's a design, which is basically a UART, and a DMA in there and a memory. So basically the UART doesn't have any memory. So anytime data comes in, so a UART reads in data, it has to immediately do a DMA transfer to the memory. So that's the design that we picked to show you how to create a portable stimulus model for this. And data can come in to the UART, and then you have a bunch of commands that can be, that you can input to configure the DMA and the UARTs and the memories. So what's the first step in creating a portable stimulus model? Is identify the behaviors. So let's take UART as an example and identify what are the potential behaviors of UART, right? So if you look at from a UART perspective, you're either reading in data or you're writing out data. And we qualify them or use the keyword action to identify behaviors. So once we've identified the behaviors or the action items, the next step is to identify the data flow, right? What's the data that these actions work on? And here, if you see, there is a data stream, right, which is an output of reading in action, and then you have a data stream which is which is an input to the write out action. So what's the third step? The third step is, where do these actions execute? So now you define something called as a component. A component is nothing but a namespace for you to, to associate these actions with. So by giving this namespace to these actions, you're enabling to build, components by putting multiple components together. So you're creating a namespace for this. So once you know where those actions execute, in this case, which is the UART component, we'll have to figure out what are the system resources that are actually required for us. So here, the resource that is needed is a UART resource, right? So once we have a resource, we have two action items. So basically, there's just one resource. So you need to have a lock. So whenever an action uses a resource, it needs to lock that resource for exclusive usage of that resource. So then we also we create a pool of resources. So what you see here, a pool, in brackets 1. So basically, you created a pool of one resource here, a pool of one UART resource, and then you're binding that resource, the pool of resources. When you have a star in there, that means all the actions that are in this component have access to this resource pool. That's what it means. So here's a simple component. Here's a simple portable stimulus model that we've created specific to UART. Now, let's see, let's do the same for the DMA, right? What are the behaviors for a DMA? It's, we do a U to M, that is UART to memory, or memory to UART. And then the data. So from a UART to memory action, the input is the data stream that is going in from the UART to the DMA. And similarly, for the memory to UART action, the data stream is the output. Then we also have a different kind of data object or a data which is called as a data buffer. In this case, we call it a memb, which is a memory buffer, which is the output for the action UART to memory, and it's an input to the memory to UART action. So if you see, there's the data structure on either side of the DMA. One is a data stream, one is a memory buffer. So where do these actions execute? You've got, the other thing is, in this DMA, there's another action which is possible, which is memory to memory transfer. that is from transferring data from one memory location to a different memory location. What you can see here is the input and the output for the memory, the mem to M action is both data buffer. That's the mem buffer. And where do these actions execute? Obviously in the DMA component. And what are the system resources that we need? Here is the channel. So we have one channel here. So we've created a pool of one channel, and then we are binding these actions to this channel. And then we would also have a lock of in the actions to lock the resources. So let's look at how do we define these data structures. So portable stimulus really only cares about the structure of the data, and it doesn't really care about what is really inside the data. Sometimes it does, but mainly it looks at the structure of the data. So here's how we define a data structure. We use the keyword struct to define a data segment structure. It has two variables in it. One is called as size and one is called as address. And you have a RAN variable used to define both the variables. And then you have a data type. So basically the data type helps you with the scheduling constraints of these data. So for example, if you define a data as a buffer, that means it's a sequential, it's scheduled for sequential type of access. For example, you can define, or use the keyword buffer to define a memory buffer, which is, and you can extend it from the data segment. Then you would have something called as a stream. So when you define a data object as a stream, that means it's for parallel execution, parallel semantics. So that's how you define a stream. And in this stream, you have two more additional variables, which has direction and stop bits. So let's look at the data flow. When, how can you create specialized struct objects? So one is a buffer, stream, and state. And that's the syntax for creating specialized struct objects. So like we looked at buffer. Buffer is basically used for any data that is stored in one location. It's not transient, it's in one location. Stream is for any transient kind of data. And state is to, to capture the state at any given point of time. And so that's how you define these specialized objects. And the thing to note is any of these specialized objects can inherit from a basic data stripe, but they can't inherit from one another. So here's the observed behavior. So when you have a stream, basically they happen in parallel, and that's how you use the notation, a graphical notation, to imply a parallel data being consumed. One produces it, the other one is consuming it. And basically stream is 1:1. And then when you have a buffer, it is one-to-many kind of one-to-many consumption. So there could be one producer but many consumers of it, and that's how it gets captured in a graphical format. And state is for many-to-many. So now we also have, once we have data, we need to also be able to constrain it. So we have data constraints to limit the solution space. So here's a constraint that we have, that we've added to the read-in action of the UART component. We've set the data direction to be in. So also the other thing to note is when the actions that share a data object between actions need to have compatible constraints. I said compatible, not the same. You need to be compatible constraints. So here's read-in action, which is actually producing a data stream and which is being consumed by UART to memory action. So now if you see the constraints, we've given the direction of both of them to be in, right? Now, the other constraint that we've added is the data size is should be the same. The source data size should be the same for the destination size. So again, this is another constraint that we've added. And for the M2M action, we've said the data size should be the same as the source, and the destination data size should be the same. But the other thing that we've added is that the source destination address and the source address and the destination address shouldn't be the same, because you're writing memory to memory transfer and the location can't be the same. So here's a simple example to show you how constraint narrow this solution space. So here is a buffer, a data object, which is mbuff, which has 4 bits of bit value, which is x. And we have 3 actions, do B, do A, and do G. So right now, based on the input and the output of the buffer, we can see how they are related to each other. So let's put a constraint in the action B and say M should be less than 12. So if you see M is less than 12, then the other constraint that we've added is that M in A, that M X should be greater than 2. So now the data object that gets transferred between the action A and gets consumed by action B, you're limiting the state space of that to be between 3 and 11. So similarly, if you have a constraint on in the action G and you say X to be greater than 8, and then you've created another buffer which gets transferred between G and B to be between 9 and 11. So now let's assume we have one more action called P. And here we've said the constraint set to be less than 8. So now, if there's a transfer from A to P and, then the mbuff gets constrained accordingly. Let's say, now if you see there's a conflicting constraints, not conflicting, if you see the constraints in action G and P, G says X should be greater than 8 and P should be less than 8. So what it means is that there can never be a transfer between G and P. So that's automatically implied. So now if you, and even you can add a constraint to your buffer as well. So that's the other thing. So now let's look at how do we assemble it at the top level. So we have something called as a PSS top, right? And now the component, the top level is called as component PSS top. We instantiate the UART component that we had. So the UART component had 2 actions and 1 resource, which is the UART resource. Then we instantiate the DMA. So the DMA had 3 actions and 1 channel resource. Then we create a pool of stream data, right, at the top level. And then we go ahead and bind the stream to all the actions and all the components that are instantiated in the PSS top. So now all these actions have basically access to this data. Then we create a pool of memory buffer. This memory buffer might have as well been inside DMA, but by instantiating at the top level, what we are doing is we are letting other components have access to it if needed. And then we bind it to all the components or actions there. Then this is where we actually create our test intent, right? So our intent is now to create a loopback test, right? So what is it that we do when we do a loopback test? We do a read in and then we do a write out, right? So now anytime we want to create a test intent, we have something called as an activity block. So activity block is where you define the flow of the actions that you have. So now what we've done here is we've instantiated the actions inside the action block of the loopback test. We've instantiated the UART read-in action and also the DMA U to M action. And then in the activity, we've used a keyword called as parallel, and we said both the read-in action and the U to M action are supposed to happen in parallel, right? And this is how the graphical representation of what you see in here, of this parallel usage of data, parallel usage of actions. And now read-in produces a data stream, and that gets consumed by the U to M action. And then what you do is you are actually binding the data, that is you're binding the read-in data to the U to M source data. Similarly, you go ahead and instantiate the other actions, because our first intent was to do a read-in, and as soon as you read in, this data gets, a DMA happens, it goes to the memory, and then you read it out, you do a DMA and write it out. So that's the intent, right? So we've done the first part using the read-in, and now we do the write-out. For the write-out, it's the same thing. Here, the memory to U or M to U action generates the data stream which gets consumed by the write-out, and we just go ahead, instantiate them, say they're a parallel activity, and then we bind the data of M to U and the write-out action. So, and then we also have the memory buffer. So when we do a U to M, a data is being created and it's being stored in the memory. So we go ahead and create that data, and that is the data that gets picked up by M2U as well. So, there's a data that is getting produced. That's a memory buffer, because this this data structure is, is going to be resident in a permanent memory location, a storage unit. So that's the reason it's a buffer. So this is how you go ahead and assemble your top level test. So what you see here is your test intent of writing a loopback test captured in a graphical format, right? So you capture it in a portable stimulus, specification, and a tool would read it and reduce it or deduce this graphical format. So what you see here is a typical, directed constraint random test that you would have created, where you know the intent, you know what, it's basically a directed test where you're just going and constraining some of the variables that you have declared as flag. So let's see what are all the, different, yeah. 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 Right. 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 So think of it as two tasks running in parallel, right? So now you can either, okay. So let's look at the different kinds of activities that are out there. So we have something called as that is an instant of an action. You're actually using an instance of an action, and that's the action traversal. Then we have something called as a do, so you can do an action in an activity. Then we have parallel, this is something that we just looked at. Then we have sequence, so we can create a sequence one after the other. Then we have select, that is this or that. Then we can schedule. So when you schedule two things, what it means is all possible scheduling schematics come into the picture. Then you can do if else. You can do repeat, and you can also do for each. So these are all the possible type of activities that you would have. So now, what we're looking at here is, this is the intent, right? Now, this is how you go and write your test cases. Now, how can we enable automation, do its magic here? Can we only specify the critical actions that are needed and let automation take over and do these things automatically for you? You don't need to go and actually specify each and every action and the dependencies. Would it be possible for you to just specify the key actions and then let the tool, the automation, come up with all possible scenarios that are out there for you to come up with, and look at all possible scenarios based on the system resources that are available, based on the constraints that you have set, based on the actions that are available and the data flow dependencies that are there. That would be an ideal world. You need not want to specify each and every test flow like this. You identify the key, key actions and let the automation take over and come up with the entire set of, or legal set of, various scenarios. So here, what can happen is, if you think about it, you can actually get rid of the data, because it's quite implicit that when you have data reading in and there's no buffer, it has to be DMA'd out, right? So the data flow is basically implicit. So what we are trying to do here is get rid of all the implicit stuff and say only what's explicitly needed. So when you do a loop back, what are the two explicit steps that you need? Reading in and reading out, right? So can we get rid of all the other things and let automation take over here? So now if you think of this as well and say the two key activities or actions that I have is read in and read out, right? And now if you let the tool take over, or automation take over, what happens is this is what gets realized or inferred. Because now between a read and a write out, there could also be a M2M action that can happen. So this is how you let our automation take over. So now how do you map these execution, map these action items to actual execution is using the execute blocks. So when we have an action called as read in, so you can basically target using these execute blocks, you can target to either a C or a SV template. So here what you're seeing here is this execute block targeted for C, and we have these mustache notation to refer that these are PSS fields. And what you see on the right is the basically the C code and the mapping of this execute block to the actual C code. So this can be SV as well, right? It's the same. So you can either target a SC or an SV. And what you can also do is if you have existing code, you can actually go ahead and import that. You can import these external procedures by using a first an import keyword, importing those actual task names and then using them. But now you see the difference in the execute body. There are actually no mustache braces that were used earlier because you're actually going and importing that code. So what we need to keep in mind is execute blocks can be only defined in leaf level actions. So you can't have an activity and an execute body in the same setup, in the same activity. Yeah, yeah. Exactly. Yeah, yeah. It's a methodology. It's part of the methodology. It's part of the standard. It's part of the methodology.
Basically, for those who know, we inserted aspect-oriented into that language. For those who use, that is part of it.
Aspect
More
is
like
here.
the E. In UVM, we inserted factory to resolve that, but that is not. Yeah, we were trying to match.
You got him excited now. So in summary, we've actually defined the component blocks for the DMA and UART. Then we put together a top-level PSS component, and then you let automation take over or a portable stimulus tool for you to realize the graph based on that, and then you basically can either make it you can target it to a C environment or a SV environment. And with that, I would let Sharon on the stage.
So the randomization is happening before the code is written?
You can do both. You can generate code, or you can do randomization on the fly. You run with a platform that allows you to do that, you can do both. We'll talk
You
about
can control what you want to
the
do.
realization section. We'll talk about it.
I have a question, Pradeep.
Yeah.
So I've seen that from the code you dump out this flow diagram. From flow diagram you upload the output.
Yeah.
So can it be, because it is error from you write this whole bunch of code, but if I create this flow diagram on the left side, from there you dump out this code and let me verify or you to verify, and eventually dump out the C or system developer in this code.
So
Right.
yes.
Easier to dump out this one, the create this one, schematic versus writing the technical code.
So you can do both actually. So so it depends. So you can either create things from scratch, or you can import what you already have and create that graph, and then you can modify that. Yeah.
If I want to do brand new environment, can I start from this schematic diagram?
So this is a cool capability. It's not part of the standard. We didn't choose graphical notation. We just used ASCII. But if your vendor allows you to do that, then yes, you can. Just to say something about the reverse thing, if I start here, the semantic of the root of what's legal and what's not is not here.
I'm
So,
okay with this one.
but at the beginning I was confused that we talk about this. But yeah, this is more of a tool capability. The standard itself is ASCII format. For the same standard, we have two input formats, and you can choose whatever you want. But yeah, if your vendor decided to provide you can see that this is sort of the UML activity diagram. If your vendor decided to support that, that would be great. We know how it could be a challenge in UVM when people need to learn how to write sequences, then people will use that and choose not to write text. So but that's not part of the standard. Okay. I will not answer vendor-related questions.
Offline.
We can answer that.
Offline.
I have a good answer for you, though. Anyway. Okay. I'm going to use the building blocks that we've seen before and see how we utilize them moving forward and how we create a system-level scenario. So both reuse and automation. And I chosen to start with the same. This is the same UART model that we've seen before. So we have a UART which is enabled by a DMA here. And this is what you do if you build a UVM environment, right? We'll build one agent, VIP per interface. We'll have a library of sequences, and we'll have virtual sequence for the multi-channel control. We can set up coverage and do exhaustive testing. Works. It works very well. Now I want to take it to the next level. So the next level in our case, we maintain our design to be device to be exactly the same. We just put things on top. So we have compute subsystem in this case. We didn't have to, but we have 4 cores in here in one cluster. We have a crypto device that can do encrypt and decrypt, and we have some graphic subsystem. So here's what we did, and I want to touch where there's misconception about reuse. What happened to the virtual sequence right now? We cannot control the bus side of things. The external interface for the subsystem become internal for the larger system. We cannot reuse that. So the entire sequence library that we built, I cannot shoot. So the entire sequence library that we built here is not valid, and the virtual sequence is not valid. About the UR device, which remain external to the full system, I may reuse that in simulation. In emulation, as we heard in the panel, you start losing performance if it's the same UVM device. But if I go to really fast platforms like ICE, like FPGAs, post silicon, that's not going to fly. So how do I enable this kind of reuse? And I've seen this kind of project of users trying to enable this scheme on top of UVM, which doesn't work. But I want to talk about something else, about what do you want to reuse in the next level of thing. And I'm going to use a story for that. Anyone knows who Steph Curry is? Steph Curry? Less than a half? Okay. Steph Curry is a basketball player, one of the best in the world. He's playing in the Golden State Warriors. He's the best shooter and probably the best dribbler in the NBA today. And he has this awesome drilling practice that he tries on his own using one basketball or 2 basketball, and the audience loves to see that. Very entertaining. But when the Golden State Warriors do a team practice, do they all watch Steph Curry do the same thing, like over and over again? No. They're going to practice team coordination, defense, offense. System-level scenarios are the same. Yeah, I might decide to run the same scenario that I tried in a subsystem, but really I'm going to desert exhaustive testing that I did in the subsystem, and I'm going to address coordination and timing that is valid for my system scenarios. So this is system scenarios. Examples. Multi-IP kind of use cases. Maybe I'm reading a video from a mass storage device, and I'm going to differentiate the video from the audio and do some processing. Multi-subsystems are involved. That's a use case that I want to try. Stress the performance. I'm having an interconnect and a memory, and now I'm sending traffic in parallel, legal, in coordination to stress and check my performance. That's coordination of multiple devices. Low power. I want to low power the entire system. I need all the subsystems to go down at the same time. And if the PCIe is going to start sending traffic, it may wake up the system, not what I want to get. That could be a very hard challenge to coordinate all this power shutdown on the entire system. Coherency, exactly the same. These are the kind of scenarios that you will have to use in system level, and these are very hard to coordinate. They're different challenge to do, even if you try to use UVM approaches. So how can we enable this kind of view? Multi-channel, state variables, etc. And the solution, I'm trying to build tension here, PSS. So how does PSS does that? So there's two steps. The approach has two steps. Kind of seen that in the subsystem level. I'm just going to repeat them, but they're the same as was described before. The first thing is to define the actions that we have in the full system. And this is composable. Whatever you defined in the subsystem before is usable, is valid. Go ahead and use that. It's valid to be used. What's unique about the actions, as we've seen before, is that they have composition rules. The actions can say, oh, I'm a capture of a camera. I'm outputting a buffer to memory. That's what I'm doing. The transfer of the DMA is saying, oh, I'm reading a buffer, I'm writing a buffer, and by the way, I'm consuming one of the resource channels that you have. Could be one or more. What we're doing here is we're describing to the system, instead of us doing it, keeping it on our head and do it with our fingers, we describe the legal scenario space. And we give it to a PSS compatible tool. Here's the rule. Here's what's legal. Here's the amount of resources you have. Any configuration consideration to running some activity, you can write it down in PSS. This is the configuration. You need to be in mode A or mode B in order to write that action. These are the composition rules. Step number one. Step number two is to compose the activities. As was described before, this is the things you can put inside the activity block. And you can do parallel, and you can do for, and you can do everything you want to do in C or in UVM. But the key thing here is that the PSS tools know what's the legal limitation. So it can tell you, if you try to run these two actions at the same time, you don't have enough resources to run them. Even if it's compound, even if it's complex, we're talking about system level, the tool can go all down the way, down to with the analysis, and tell you there's not enough resource for that. And if there is enough resource, it will make the right split of the available resource to make a legal scenario. And if an action requires the power to be down or up on a certain domain, it will make it. It will insert an action, right? It will make the inference and implication to turn on that block and to enable that activity that you wanted to get. This is how you achieve very hard to achieve, very complex scenario that requires a lot of coordination and state machine calculation. Give it to the tool. The tool will create it. This is the automation that we achieve. Now, we already discussed the modeling. I'm just going to show you that it's exactly the same. And here's the UART, the write out and the read in. Here's the DMA. We've seen that. This is totally valid. Notice that I didn't say in here who provided to the mem-to-mem action, who provided that memory. It could be a bus master that did that, but it could be the CPU compute subsystem that did that. That will work, right? Totally isolated. These actions are totally isolated, well encapsulated. They don't assume anything about their surrounding environment and activities. That's what we're doing here. Here's just another example of a crypto engine. And you can see a little bit of what we're doing here with constraint. So the crypto engine, it's very hard for me to read, but the crypto engine can do encrypt and decrypt. You basically read from the memory and write back to the memory. And we have some constraints about the 128 blocks. So this is all just constraint on the input and the output, right? I can put constraint on the configuration. I'm reading in the configuration, I'm putting constraint about what I need the configuration to be in order to execute that specific action. Okay, the tool can take that into account. We'll see an example with a state variable. And because I cannot do nested encryption, I'm just saying the source should not be encrypted, that's as a constraint, and the result is encrypted. Okay, yet another constraint to reflect what I'm doing to the data that is traversing. Again, we're describing what is legal, and this is just saying something about the abstraction and the encapsulation nature of these actions. Notice as well, and this was said before, we don't assume anything about the implementation. That is secondary. Whether I'm going to call register sequence to do some configuration or a firmware routine in C, or it's going to be TCL even, I don't care. It's part of the standard. The standard allow you. We don't know what your API is, of course. We don't know what languages you use in your test benches, but we give you a way to teach the tool how do you implement for your specific test bench, how to implement the generated code. Here's just another example of modeling of the compute subsystem. At some point, of course, the CPU cores are going to be inside. How would you model a compute subsystem? So here it is. We have used inheritance in here. We already said we support both aspect-oriented and object-oriented. In this case, we show inheritance of actions. We define an abstract action, which is a software operation, which just means if the core is executing something, we're basically locking the core. The approach allows you to do multi-threading on the same core. In this example, we're limiting that. This is what we're doing here. There is a resource of a core, and we're locking one of the core to do any software operation. And from that, we derive the various operations. So we have inheritance in here. The check data derived from software operation, and the check data is reading a source buffer. That's what I'm doing. That's an input. Okay? The next one is the write data. I'm outputting a memory buffer. So if I want to generate now a DMA transfer, it might be randomized that one of the cores will do a write, so the DMA transfer will take place. Okay? Pre-condition and post-condition. And we have a copy data which looks somewhat similar to our DMA transfer. I'm reading, I'm writing, I'm locking the core by inheritance. And by the way, the size is the same because we're talking about a copy operation. We're not touching the data. And you can actually create structure and hierarchy for this compute subsystem. And this is what we're doing here. We instantiate these cores on the top. This is what you see in here. By the way, the binding, why do we have the binding? The actions are doing input and output and getting resources, and where do they come from? This allows you, the user, coming from above to say, here's the resource, whoever is below me, whatever action is executed below, here's your resources, here's your state variable, here's your memory, okay? This is how we maintain all the logic reusable, and as integrators, you can specify what are the resources that are available for these actions, okay? So it's also a way to enable reuse. And what you see below, it's hard for me to point in this setup, here we go. And what you see below is just a structure. We built that from enumerated type. See how simple it is? We basically have enumerated tab for the cluster tag and the core tag, and we're just saying, well, if you belong to cluster A, then your core tag is A0 or A1, and if you're B, B0 or B1. And we just described basically 2 clusters and 2 core for each cluster. So that's kind of the attribute that we use. And now the second step. This is where we harvest, right? We create that model, and now we can do easy test creation. This is just a simple one. You wouldn't see the value yet, but it's because it's very, very directed, you can say. So what we have here is we have a write operation, then encrypt, copy, decrypt, and check. You can see all of that here, right here. And this is the binding. We even specify appropriate, correct status of the memory. Here's how you do it. The activity is write, and I want to write to a cacheable region. That's just one constraint. And then repeatedly, parallelly, do copy, and I want basically to use a different core. So I selected instance ID. That's an attribute that you can choose for resources. So make it different than the first one. And run a transfer, both of them in parallel. Okay? I didn't specify which memory, what's the location of the region, which core is going to be executed. There's 4 mains running in parallel in here. That's going to create a legal scenario, and this is the kind of the UML diagram that you're going to get from it. And you do that repeatedly, right? Exercising your coherency protocol. You can create millions of these. Okay, so for full system, if coherency is a challenge, both I/O and cache, we have the solution for you. And again, could be realized with the core or without the core. That's up to you. Now we did everything we did, yes. Let me repeat the question, and I'm going to pretend that I didn't ask you to ask it. No, I'm just kidding. So the question was, let's say there's multiple ways to get from one place to another. Can I constrain the tool, or someone instruct the tool, hey, find the closest path to where I want to go from here? And the answer is definitely yes. The tool knows all the possible transitions, and it can actually find the minimal path, or you can say, oh, you can go beyond that path. The semantic of PSS allows that. The various vendors will have to support it, but definitely there's tools doing that. Okay, now we have, enhancement to our enhancement that we just added to our design. We were told that we have a low power conditions that we need to support as well, not just a functional test. As you can see it here, here's the description. The crypto and the UART belongs to domain A, and the domain B has the graphics in it. Each one of them could be either active S0 or in sleep mode, S1 or S2. If you want to activate the UART or the crypto, domain A must be active, S0. Okay? That is what we're trying to achieve in here. So how would we address that? And here's where the aspect-oriented will kick in as well. So A, we're going to model the low power challenge. And I don't know if it was said here, we have a lot of usage examples that we use in low power, get at least 3 or 4 usage examples because it's a very big problem out there that PSS can solve. And here's how we did the modeling. We have enumerated type S0 to S2, and we create a state variable. PSS have the notion of a state variable, and we have 2 domains, A and B, which could be either in S0, S1, or S2. Initially, they're all going to be active. They're going to be S0. And here's a way for us to create power transition. This could be calling some management unit to do the transition, or maybe calling a register sequence. We don't care at this point. The only thing we care is, look, the change power state is reading the power state and is outputting the power state. At this point, there's no, we can move to wherever we want. Sometimes it's not the case. You can only move to some areas within the state machine of your power. But that's what we have. So state object, aggregate system power state. The enums are here. Both domains are active initially. Here's the transition action. There's just one. And here's the PSS stop. And you can see that we extend the PSS stop because everything we created before, all the instances are valid, and we want to keep them there. And now we want to introduce the power aspect to the existing action, right? So here's how you can do it. And again, the aspect-oriented. Extend the graphics decode. Make sure it's reading also the state, the power state. And here via constraint, we're saying for decoding, domain B must be active, must be S0. We're saying the same thing for encrypt. Domain A must be active, S0. And now we can create scenarios. This is the modeling part. We're done with that. Now we can create scenario. So for warm-up, if I want to say this is my activity, change the power of domain A to be not active, so different than S0, and then do encrypt. But we know that encrypt must have domain A to be active. So the tool can do, and you can change that, the tool can do one of the following. A, it could give you an error message saying, hey, you're asking for something illegal. But you can allow the tool, and it has the semantic, to infer that there's missing activity in here. And it will insert another action that will turn on domain A to enable what you wanted to get. Okay, so the description here is very short, mapped very nicely to what's written in the verification plan. It's partial. It doesn't list activities that, they're just details that, didn't make it to the verification plan. And the tool can auto-complete that. And looking at another example, we also support, we kind of said that, inheritance is supported. And this stopped moving. And here's another example that we do a lot. Here's random traffic, which could be either copy, encrypt, or the graphics will do the code. And now I want to do power with traffic at the same time. Okay, so repeatedly, 2 times, I can go 20, I can go million. Change the power state or do random traffic. There is relationship between them, right? There's coordination. I cannot just do whatever I want because it's related, to the state of the power. So this is what's going to take place. Initially, everything's going to be active, remember? Initial, active. And then we're going to select, change the power to something. This stopped moving. Okay, A is now not active, so encrypt is out of the picture. So it's going to select just the random traffic that are legal. And we're going to do another change, and it's going to do another selection which is legal, and you can play and create this random chaotic test that is legal for your post-silicon execution. So yeah, this ability, we mentioned that before in the subsystem, the ability to analyze all the scenarios, including the request and the modeling to achieve legal scenario. And this is where PSS takes the solving really to the next level, and this is where we come to our summary. From out of the door, PSS has the DNA to create this reuse. The actions are well encapsulated. They don't assume anything, not on implementation, not on activity or behaviors that going to enable one activity. You can think both about bottom-up, but also about top-down device reuse. So the top-down guy can tell the subsystem guy, here's scenarios here's the activity I'm going to do. Run them on your UVM environment. No,
schedule an action to execute first, right, in the list of all the actions that are possible. So that you can certainly do. But when that runs, what is required is actually the set of registers the device implements needs. Someone has to go program, set them up to legal values and so on and so forth. That you can do using HSI.
Generate the different possible configurations to start with, right? So
But then here say different, the protocol will remain the same, but the implementation of the protocol can differ from the architecture specific point of view, right? So I have a register space, I have different set of memories. So the memory designed by Intel could be different from the memory space designed by AMD, for example. So how is the architecture dependency held, taken care in this case?
that the user needs to define, because as you correctly said, it's dependent on the various users. You may use it or define it differently while he may define it differently. So it's the user who has to define for his use case where is the different register memory space, while for another user it's different.
That's the whole reason why there is composition and inheritance, right? And what you have to do is design it with certain intent in mind. What the committee here is going to provide you is with a bunch of standard language constructs that will allow you to architect it. But just because you write bad code doesn't mean that the tool will solve it.
Not about bad code. I'm saying is the entire flow, where does it fit in? Like if I want to program an IP, right, I want the initial configuration of the IP to be up, where would I put it in the entire flow?
So let me try also to answer it. Essentially, I think it's the same thing. So the question is like this. Do you want this configuration to be changed as part of the solving? If you want this to be changed as part of the solving, you need to put it in the solving layer and isolate at this point the implementation layer, whether you're going to use HSI or not. Because you want to change that, and maybe actions, you typically will create it's an abstract memory. It's not real memory. It's a virtual memory that you need only for the solving. And multiple actions will look at it and say, what is the value? Is the value matching what I need to be executed? Okay, so that's solving part. That's not realization yet. Then there is the realization session. Now, the question is, what do we want to put out there? It's a question valid for UVM. If I would ask, where would you do that in UVM? I'll get multiple answers. That's realization. You want to take configuration that are essential for your simulation. For SOC level, we're not randomizing all the registers in SOC level, right? There is some attributes that we want to change for our SOC or high-level simulation. Put that inside a control flow, the data structure that we discussed. Put constraints on what is legal, and now you can have dependencies of actions. Oh, I need the configuration to be like this. I need the configuration. That's not going to be coded in any way. There's no memory really to represent that. That's for the solving. It's a design pattern for solving in PSS. You can have a state variable as well if you can do reconfiguration, right? If one action can reconfigure. So you read the current configuration and you can reconfigure with the prev and next. So that's the solving layer. Beyond that, use whatever. You're probably going to use either HSI or firmware that will change the configuration. That's up to you, I hope. Right. The nice thing is, right, it's the bidirectional nature of this thing. You can change the configuration, that will change the traffic. You can ask for specific traffic, that will change the configuration, and that's